Here is an example of how hot electrons can turn an impossible reaction into a reality. The graph on the right shows a hydrogen molecule adsorbed on the surface of a gold particle, where the two hydrogen atoms in the hydrogen molecule is separated by 0.74 angstrom. To break them free, we would need to vigorously shake them apart by interatomically injecting 4.52 electron volt worth of atomic kinetic energy to stretch the interatomic spacing to the breaking point. Then they break free. Now, if we use heat on a classical mechanics scale to generate that amount of kinetic energy at the interatomic quantum mechanics scale, the temperature at the classical mechanics scale would rise to more than 34,000 Celsius according to the kinetic temperature formula shown in the bottom of the slide. As known, the concept of temperature exists only for large groups of molecules at the classical mechanics scale. So, a rise in the temperature to more than 34,000 Celsius would translate to the desired 4.52 electron volt at the interatomic scale. The problem here is that the gold melts at 1064 Celsius, meaning if we use heat as a means to increase the atomic kinetic energy by 4.52 electron volt, the gold would melt long before we get a chance to hit that interatomic kinetic energy target of 4.52 electron volt. This makes that reaction an impossible reaction. That impossibility is turned into a reality when the required 4.52 electron volt increase in the atomic kinetic energy does not come from a thermal energy input, but rather directly delivered by highly energetic electrons, also known as hot electrons, impinging on the hydrogen molecules. This way, the splitting of hydrogen molecules unprecedentedly took place at room temperature. The use of hot electrons bypassed the need to raise the temperature to thousands of Celsius degrees. On the left side animation, there is a demonstration of the interatomic bond for hydrogen molecule being stretched to the breaking point under the exposure to the highly energetic electrons.